Hi everybody. This video is going to be on section 9.2. This is laying down more theoretical groundwork for this chapter. It's called vector formulation. Okay, so the whole idea of this section is that we can take any system of differential equations that's linear and turn it into a vector space problem. Our whole point here is that we're trying to connect this with what we already know about vector spaces. So we can formulate a first order linear system into a vector space problem. So here's how, right? Remember we had all of the derivatives and I don't want to write everything out, but remember this all goes on and on and on, right? We've got, lots of stuff on both of these, okay? So here's what we can do, right? We can take all of this and we can write it as follows, okay? So this whole thing that we wrote down becomes the following. X prime of t is equal to a of t x of t plus b of t. Where? So what are all of these things? So x of t is just going to be the column vector of functions. So it's x1 of t all the way to xn of t. So we take all of those guys and we put them into a vector. And of course, the derivative would just be exactly that, x1 prime of t. It's the derivative of all of the individual component functions in there. So that's x prime of t and a of t. This is maybe the most important part. A of t is going to be exactly that, and this is what we call the matrix of functions. Okay, think of it as the coefficient matrix, right? And we also have one more, right? We have, I should mention what b of t is as well, okay? So b of t, let me just put this on the next line since we're out of space. And b of t is exactly b1 of t all the way to bn of t. Okay? Okay. So this is how we formulate a system. And we're going to be talking a lot more about this vocabulary in this section. So where is the vector space? Let's go ahead and define the vector space that we are talking about. So we're going to define Vn on I to be exactly the set of all column n vector functions on I. So note we do have addition in this, right? How would you add two of these guys in the vector space? Well, as you can imagine, we just add the functions one by one. Oh, that should be a t. Let me make it look a little nicer. Okay, so you just get a brand new function, and of course, if you want to multiply by a scalar, you can do that. You just multiply each guy inside each function by the scalar to create a new function. And so these two facts tell us that Vn of I is a vector space. In particular, it's an infinite dimensional vector space. Anytime you have functions involved, there's no way to write a finite basis for it, okay? There's no way to build all functions that exist out of a finite number of functions, okay? But this is an infinite dimensional vector space. Okay? So we need a new definition. We're translating a lot of the terminology that we know into this new vector space, okay? So let's suppose now that we have n of these vector functions, okay? Let x1 of t all the way to xn of t be vector functions, Vn of I. Then the Wronskian of these vector functions is, so this is how we write it. This notation might look familiar to you because you still take all of these functions and you put them in here. But here's the catch, okay? Remember, this is a determinant. Before, what we had to do is take lots of derivatives, but we don't do that now. What we do is we take the determinant of, we just take each one of these and we make them columns. Each vector becomes a column of this matrix. So this is an n by n matrix, so we can take the determinant of it. Okay, so I will say note, for vectors, no derivatives are involved in the Wronskian. Okay, this is important, okay? You can take the Wronskian of vector functions by just making them columns and doing your determinant. You do not have to take any derivatives. So, what is the conclusion with Wronskian then? Why are they important? Well, you can imagine they usually have to do with linear independence, and it turns out that is still true, okay? So let me write out the theorem on the next page. So suppose that we have x1 of t x to xn of t, and let's suppose that these are all living in this vector space. Here's the theorem. If the Wronskian of all of these guys of t naught is not 0, at some point t naught in I, then those vector functions x1 all the way to xn, this set is linearly independent on the interval I. So what is the proof? Because this theorem is not difficult to prove. So let's suppose that C1 all the way to Cn are scalars such that C1x1 plus Cnxn is equal to 0. Okay, what does that mean? So this implies, so we can actually formulate this as a matrix problem. So if we put those all as columns in a matrix, then what this is saying is that that times this is equal to 0, right? And we're saying that this is equal to, we're saying let's suppose that this is equal to 0. Now, if the Wronskian is not 0, then this must mean that the determinant of, if we were to call this entire matrix right here, capital X of t, then this means the determinant of capital X of t is not 0. But what does it mean for that determinant, for that entire determinant to not be 0? It means that the only solution is the trivial solution, right? And this implies that C1 is equal to C2 is equal to all the way to Cn. It means that they're all 0, which implies that the set is linearly independent. Okay, so it's actually pretty straightforward, right? This just has to do with how we set up systems and what the determinant implies when you have an n by n system of equations, right? So let's do an example where we try out this theorem just so we can practice checking linear independence here, okay? So example. Let's let x1 of t be e to the t and then 2e to the t. And let's also let x2 of t be 3 sine t and then cosine t. So question, are they linearly independent on the interval -infinity to infinity? So what we're going to do is we're going to do the Wronskian, right? We're going to do the Wronskian of x1 and x2. What this means is we're going to take the determinant of a 2 by 2 matrix, right? It's going to be the determinant of, we're going to make these column vectors as columns of our matrix, so 3 sine t and then cosine t, right? We're going to do the determinant of that guy. So what do we end up with here? We end up with e to the t times cosine t minus 6e to the t sine t. Okay, and what do we know? Is this 0 everywhere? Well, clearly not, right? This is not 0. For example, let's say at t equals, all you need to do is find one point where it's not 0. So how about t equals 0, for example? At t equals 0, what is it equal to? It actually is equal to 1. So it's definitely not 0 everywhere. What does this imply? This implies that x1 and x2 is a linearly independent set on -infinity to infinity. Okay. So it is quite easy to use this theorem. All you have to know how to do is take a determinant, right? All right, so let's go over a few facts, okay? So given an n by n matrix function, A of t, and given x of t in Vn of I, the following maps are linear transformations. So what are they? So first we have something called the T-map, and the T-map takes Vn of I to Vn of I, and it's given by T takes x of t, and it takes it to A of t times x of t. This should look very familiar, right? Remember, in regular matrices, we said that T of V is equal to A times V, that this is a linear transformation, right? Left multiplication by a matrix. What we're doing, this is basically the function equivalent of that, right? Instead of Rn, though, we're talking about Vn. Very similar, it's just it's just column, instead of being an n-dimensional column of real numbers, it's just functions. That's all it is, right? The only difference. So that guy is a linear transformation. And also, let's call this guy D. D takes Vn of I to Vn of I, and this is given by D of x of t is equal to x prime of t. Both of these are considered linear transformations because they carry over addition, right? Remember the linearity properties? So they distribute over addition, and a scalar does not affect the outcome. It just gets multiplied by the scalar, right? And that just has to do with how derivatives work. Okay, so both of these are linear transformations. That's what these facts are telling us. So now let's define what a vector differential equation is. So definition. A vector differential equation is something that looks like this, okay? And I'm going to go ahead and I'm going to call this guy star. Okay, this is just a reformulation of what we saw in the last section. Okay, we can take all of it and write it in a nice simple form like this. So what is our goal then? Our goal, of course, is to find all x of t in this vector space that satisfy the differential equation. So I'll just say that satisfy star. So that's what it means to solve one of these, okay? Rather than looking for a regular function, you're looking for a vector function that satisfies them, okay? So also, a homogeneous vector differential equation is something that looks like this. X prime of t is equal to A of t times x of t. You notice there is no b of t, or another way to think about it is that b of t is equal to 0. B of t is equal to the 0 vector, right? It's just not there. Okay, so we have a vector differential equation. This is our definition of that. And then we have a homogeneous vector differential equation, and that's the definition of that. Now, as an example, I want to go back to a problem that we solved in the last section, and let's reformulate it with vectors so that we can see how this can be written, okay? So, example. In the last section, we solved the linear system x1 prime is equal to x1 plus 2x2 and x2 prime is equal to 2x1 minus 2x2, and the general solution was so we had x1 of t equals c1 e to the negative 3t plus c2 e to the 2t, and x2 of t is equal to negative 2 c1 e to the negative 3t plus 1/2 c2 e to the 2t. So look, this was our system, and this was our solution, right? This is what we found in the last section. So we're going to do a vector reformulation of this. So vector reformulation. Okay, so what we're going to do is we're going to rewrite it this way. X prime of t is equal to 1, 2, 2, negative 2 times x of t. Or if we let a equal to 1, 2, 2, negative 2, then we get the following for our differential equation. X prime of t is equal to a times x of t. Okay, so if I were to call this guy 1, I have reformulated 1 to look like this. Okay? So what is our solution then? How would we write this in vector form? So notice the solution. Here's what we got, right? We got x of t is equal to, I'm going to go ahead and write it as a vector, okay? Our top guy, our x1 of t, is equal to e to the negative 3t plus c2 e to the 2t, and then we also had negative 2c1 e to the negative 3t plus 1/2 c2 e to the 2t. Okay? But isn't this the same as c1 times e to the negative 3t negative 2 e to the negative 3t? So all I did was I pulled a c1 out of the first guy plus c2 and then e to the 2t. Oh, yes, e to the 2t and then 1/2 e to the 2t. Okay, so this is what we get. So what is the solution set going to be then? The solution set is going to be the span of those two vector functions. Okay? Now, you could go ahead and do the Wronskian test, but these two are two linearly independent solutions to star, or actually let me call it to, let's see, we called it 1, right? To 1. Okay, so this would be how we take the solution. So if we go back, this solution, if we call this guy 2, right? 2 is the solutions, then the way we would write it as a vector is either like this or like this, right? Both of these are the solutions. This is how we would write it as vectors. And by the way, because it's the span of 2 vectors, then this is equal to a 2-dimensional subspace of V2 of I. Right? It's V2 because there's 2 elements in each one, and it's 2-dimensional because there's 2 vectors in the set. Okay? So this would be a vector reformulation. And that's all there is in this section, because this is just laying some groundwork for the following sections where we start to actually learn some techniques for solving these things. Okay? All right, guys. Thanks so much for watching.